Hello students, I am Laxman Singh Rawat, PGT Chemistry at CIS Dasua. Students, I hope you are enjoying this method of teaching learning that CIS Dasua has come up in this hours of crisis. CIS Dasua's e-learning is helping students to study at their home so that they do not lag behind due to this lockdown. Students, I hope you have seen the previous lectures. Now today also we'll continue with some basic concept of chemistry. Today we will start with an important concept of chemistry, that is the mole concept. We will solve a few numerical based on the mole concept, and then you will try some examples at your home also. Before we start today's topic, let us take a quick recap of previous topics. The topic was percentage composition and then empirical and molecular formula. Let us start the day with discussion of the topic percentage composition. Now, why do we require this percentage composition? At time we are given the percentage composition of different element, and we use this percentage composition of these different element to find out the formula of the given compound. Okay. Also, we may use this percentage composition to find out the purity of a sample, and this is found out by mass percentage of an element is equal to mass of that element to the molar mass. Now let us try to understand the empirical and molecular formula. After that, we have understood what is the mass percentage of an element. In fact, the mass percentage of an element can be used to find out the empirical and molecular formula. First, let us discuss what is empirical formula. In fact, empirical formula represents the simple whole number ratio of the various atoms present in an element. An example has been taken here, that of glucose, C6H12O6. This is the molecular formula, and the empirical formula is CH2O. That means when we divide the actual number of molecules by the HCF, we get the simple whole number ratio between all these elements which are present in the given molecule. So for glucose C6H12O6, the empirical formula is CH2O, which shows the simple whole number ratio of different elements. Now, what is molecular formula? In fact, molecular formula shows the exact number or the actual number of different type of atoms present in a molecule of a compound. Here we have taken example of ethanol C2H5OH, which is the molecular formula, and the empirical formula of this one is C2H5OH. In this case, the empirical formula as well as the molecular formula remain same, since they cannot be simplified into a simpler ratio. So in this case, the molecular formula and the empirical formula both will be same only. Now let us see how we can find out the empirical and the molecular formula. If we know the mass percentage of different element present in a given compound, then we can easily find out its empirical formula. Further, if we know the molar mass of the compound, then we can find out the exact molecular formula also. The relationship between the molecular formula and the empirical formula is molecular formula is equal to n time of the empirical formula, because the empirical formula is the simple whole number ratio of the different element present in a given compound. So if we multiply it by n, we get the molecular formula, which gives the actual number of the different atoms present in a given molecule, where n can take up the value 1, 2, 3, 4, anything. And how do we find out this n? N is equal to the molecular formula mass, that is the molecular mass of the given substance, divided by the empirical formula mass. This will give us the value of n, and from the value of n we can easily find out the molecular formula by multiplying the empirical formula with n. Today we'll do stoichiometry and stoichiometric calculations. The word stoichiometry comes from two Greek words, stoichion meaning element and metron means measure. In stoichiometry, we deal with the calculations involving the reactant and the product. Basically, it gives the quantitative relationship between the reactants and product. These relations can be in various terms. There can be mass to mass relationship, there can be mass to volume relationship, or there may be some other relationship between the reactant and the product. Before we understand how to calculate the amount of reactant or those of the product required, we need to understand that a balanced chemical equation is must for the stoichiometric calculations. So we need to understand how to balance the equation first, then we will be able to solve the questions based on the stoichiometry. For the stoichiometric calculations, in fact, whatever the information we require, we get it from the balanced chemical equation. Here we have taken example of combustion of methane, and the reaction is written as methane burns in air or oxygen to give carbon dioxide and water vapor. This reaction we are already aware. We have already done this type of reaction in grade 10th also. Okay, so we are taking example of that only. So methane is CH4. It burns in air or oxygen O2 to give CO2 plus H2O. Now we have balanced the equation also. We have put 2 in front of O2 and 2 in front of H2 so that the entire equation become balanced. The atoms on the left hand side and the atoms on the right hand side, they are equal in number. Okay, so this is your balanced equation. Now here, these numbers which are in front of any of these chemical substances, they represent the numerical coefficient, and here we call it as the stoichiometric coefficient. Okay, so we have got 2 in front of O2. Similarly, in H2O also we have got 2 in front of it. Okay, these are the coefficient of stoichiometric coefficient of O2 and H2O. And in front of CH4 and CO2, the stoichiometric coefficient is 1. Okay. Now, what do these stoichiometric coefficient indicate? Yes, we have got slight idea of this one. We already know this. They not only represent the molecules, they also represent the number of moles taking part in the reaction. Now, how to interpret this one? When 1 mole of methane burns in 2 mole of oxygen, we get 1 mole of carbon dioxide and 2 moles of water vapor. This is what we interpret from the balanced equation. Okay. Now, these can be converted into any type of quantities that we have to find out. For example, we can draw out a mass and mass relationship between these different quantities. We can find out the mass and volume relationship between these quantities, or we may find out the volume and volume relationship between these two quantities. Okay, these two quantities can be any one of these. It can be reactant only, it can be reactant and product, or it can be your only product also. Let us start solving numerical based on the stoichiometric relations. First of all, we will carry out the mass and mass relationship based questions. Okay, here in this type of questions, the mass of a substance is given and you have to find out the mass of another substance. Okay, so these type of questions are called mass and mass relationship based question. The question is, calculate the amount of carbon dioxide formed by combustion of 8 gram of methane. Here the carbon dioxide is asked in gram. What is the amount of carbon dioxide, okay, formed in gram by the combustion of 8 gram of methane? Now first of all we will require the balanced equation. So we have written the balanced equation, CH4 plus 2O2 gives CO2 plus 2H2O. Okay, and from this balanced equation we will get the quantitative relationship between the two required substances. Here the substances which are required are methane and carbon dioxide. Okay, and we have to draw a quantitative relationship between these two. From this equation we see that 1 mole of methane gives 1 mole of carbon dioxide. Okay, and we will make use of this fact to solve our numerical. Okay, so 1 mole is equal to gram molar mass, and for methane it is equal to 16. Gives 1 mole of carbon dioxide, and the gram molar mass of carbon dioxide is 44 gram. So in place of 1 mole we have written 16 gram and 44 gram respectively for methane and carbon dioxide. Okay, if we know for 16 gram we can find it for 1 gram also. Okay, so 1 gram of methane gives 44 upon 16 gram of carbon dioxide using unitary method. So if we know for 1 gram we can find it for 8 gram also. Multiplying on both the side by 8 we get the mass of carbon dioxide formed as 22 gram. Okay, these numericals are simple unitary based numericals. You may use some other methods also, but since you are already aware of unitary method since your junior classes, so it becomes quite easy to solve the numerical based on this. Now let us solve next numerical based on mass volume relationship. The question is, calculate the volume of carbon dioxide at NTP evolved by strong heating of 20 gram of calcium carbonate. Okay, so in this question the volume is asked from the given amount of calcium carbonate in gram. Okay, so first of all we will require the balance equation, that we will write calcium carbonate on strong heating gives calcium oxide and carbon dioxide. So this is the balanced equation. 1 mole of calcium carbonate gives 1 mole of calcium oxide and 1 mole of carbon dioxide. Okay, but we have to draw a relationship between calcium carbonate and carbon dioxide, so we will take these two substances, okay, and see how they are related. Since from this equation we see that 1 mole of calcium carbonate gives 1 mole of carbon dioxide, and since mole is related to the gram molar mass as well as the gram molar volume, and here we want the relationship between mass and volume. Okay, so we will convert 1 mole of calcium carbonate into gram molar mass, that equals to 100 gram, and 1 mole of carbon dioxide equals to 22.4 liters, which is the gram molar volume. Okay, so 100 gram of calcium carbonate when heated will give 22.4 liters of carbon dioxide in term of volume. Similar unitary method. So 1 gram will give 22.4 upon 100 liters. Okay, and if we know for 1 liter, we can easily, if we can find it for 1 gram, we can easily find it for 20 gram, which is asked in the question. So multiplying by 20 on both the sides. So 20 gram of calcium carbonate will give 22.4 liter upon 100 into 20. That works out to 4.48 liters of carbon dioxide. So in this question, we had found out the relationship between mass and volume. The mass of calcium carbonate was given, that was the reactant, and the volume of carbon dioxide evolved was asked, and the volume comes out to be equal to 4.48 liters of carbon dioxide. Now let us solve numerical based on volume relationship. We have got a question here. Air contains 20% oxygen by volume. Calculate the theoretical volume of air which will be required for burning 200 meter cube of acetylene gas completely. All the volumes are under the same condition of temperature and pressure. So the temperature and pressure has been held constant, since volume will change with the change of temperature and pressure. First of all, we will require a ballast equation that we have written here. 2C2H2, that's the formula for acetylene, plus 5O2 gives 4CO2 plus 2H2O. Okay. The stoichiometric coefficient means number of moles. So 2 mole of acetylene requires 5 moles of oxygen to give 4 mole of carbon dioxide and 2 mole of water vapor. According to the Avogadro law, we have, under similar condition of temperature and pressure, equal mole of gases occupy equal volume. So we will make use of this law to solve our numerical. And here in this question, we only require the acetylene and oxygen. We don't require the other two substances. So we will try to find out relationship between these two only. Okay. So 2 mole of acetylene means 2 volume of acetylene. 5 mole of oxygen means 5 volume of oxygen. And this, according to question, we have 200 meter cube of acetylene will require 500 meter cube of oxygen. Okay, so if we have 500 meter cube of oxygen required for complete combustion of 200 meter cube of acetylene, then from the question, since the air is only consisting of 20% oxygen by volume, therefore if we take 100 meter cube of air, we will have only 20 meter cube of oxygen present. So 20 meter cube of oxygen is present in air equal to 100 meter cube. So 1 meter cube of oxygen will be present in air equals to 100 upon 20 meter cube, and 500 meter cube of oxygen will be present in equals to, we will multiply both the side with 500, so 100 upon 20 into 500 meter cube of air. So this is the amount of air required for combustion of 200 meter cube of acetylene, and that works out to 2500 meter cube of air. Okay, we have used unitary method to find out the amount of 20% oxygen in air required for complete combustion of 200 meter cube of acetylene. Now let us see numerical based on the mole and mole relationship. We have got the question here. How many mole of phosphine, PH3, that's the formula, will be obtained in the hydrolysis of 3 mole calcium phosphide? The formula is Ca3P2. First of all, we have to write the balanced equation, and that is given as Ca3P2 plus 6H2O gives 3 calcium hydroxide plus 2 phosphine, 2PS3. Okay, so we have 1 mole of calcium phosphide reacting with 6 mole of water to give 3 mole of calcium hydroxide and 2 mole of phosphine. So here we have 1 mole of calcium phosphide gives 2 mole of phosphine. Therefore, 3 mole of calcium phosphide will give 6 mole of phosphine. Since the phosphine obtained is double the amount of calcium phosphide, so we get 3 mole of calcium phosphide giving 6 mole of phosphine, and this is the amount of phosphine which will be obtained in the reaction. Now we'll solve question based on mole mass relationship. We've got a question here. How many mole of iron will react with steam to give 12 gram of hydrogen? We have to write balanced equation that we have done here. 3Fe plus 4H2O gives Fe3O4 plus 4H2. That means 3 mole of iron reacts with 4 mole of H2O to give 1 mole of ferrosulfuric oxide plus 4 mole of hydrogen. Here we have to find out relationship between the iron and the hydrogen, okay, which are related as 3 mole of iron gives 4 mole of hydrogen. But we have been given the hydrogen in term of gram, so we will convert this one into gram first and see how many mole of iron reacts with 12 gram of hydrogen. According to balance equation, we have here 3 mole react with 4 mole of hydrogen, and 4 mole of hydrogen becomes equal to 8 gram. 4 into 2 is the molar mass of hydrogen, so 4 into 2 is 8. So 8 gram of hydrogen reacts with 3 mole of iron. From question we have 8 gram of hydrogen reacts with iron equals to 3 mole. Therefore, 12 gram of hydrogen will react with iron equals to 3 upon 8 into 12. By unitary method we have done it. Okay, for 1 gram of hydrogen it will be 3 upon 8 mole of iron which will be reacting. Therefore, multiplying by 12 on both sides, we have 12 gram of hydrogen reacts with iron equals to 3 upon 8 into 12 mole, that works out to 4 mole of hydrogen. So 12 gram of hydrogen will react with 4 mole of iron. Today we solved some numerical based on the mole concept. I hope I have made it clear how to solve the numerical based on mole concept. Remember that there can be various relationship between the reactant and product, okay, and a few of them we have tried. Whenever you have been asked any question based on the mole concept, first of all what we have to do is we have to see what is given in the question and what we have to find out. We have to draw relationship between these two. Unless we know how to find out or how to draw relationship between these two quantities, solving numerical will become difficult. So try some more numericals at home. I hope you will master this concept easily by practicing. So thank you for today. See you again tomorrow.